Good morning, Mr. Chairman. Good morning, everyone. Today I will be presenting to you our study entitled Polyvinyl alcohol or PVA with lithium-ion sieves or LIS, a novel reusable lithium adsorbent foam prepared via cryo-desiccation and chemical cross-linking. I am LIMJUCO of the DEST from P2FTC, Myoung University. So the following is the outline of my presentation. First, I will be giving you a very brief introduction, followed by motivation, methodology, results, and then the conclusion of this experiment. To begin with, US Geological Survey reported that for 2011, the main global market for lithium products were as follows. Worldwide, rechargeable lithium-ion batteries powered most of the cellular telephones, laptop computers, and even heavy-duty powered tools. Now, in 2011, China, Japan, and South Korea accounted for 85 to 90% of the total production of lithium-ion batteries. Now, according to a Japanese market research firm, South Korea has overtook Japan in 2011 to become the leading manufacturer of lithium-ion batteries. Now, as the demand for lithium increases, recent works have focused on its recovery on different sources, including seawater. Now, while LIS, example hydrous manganese oxide, have demonstrated its efficiency as lithium adsorbent, its powdered form renders it difficult to handle and less recyclable. Thus, membranization and granulation have been conventionally introduced to address this shortage. However, these methods compromise the lithium adsorption capacity of the LIS due to the obstruction caused by the polymer matrix. Thus, the development of LIS composite remains a challenge these days. Now, in our study, the high LIS loading of the composite foam minimizes the effect of the PVA binder. Hence, our composite is remarkably better than those other reports from previous literatures reported. Now, our composites are hydrophilic, have high total porosity, and have high BET surface area. Now, these properties comprise or contribute to the excellent performance of our materials. Furthermore, the composite is durable, it demonstrates consistent adsorption capacity, and it can be applied via absorb and squeeze mechanism, which is far more better than the energy-intensive pack bed and membrane system. So we can say that so far this study is better as compared to the previously reported in literatures. Now, to prepare the composite foams, it can be shown in this following figure. First, the dope solution with different LIS loading have been prepared by initially dissolving the PVA in the ionized water with constant agitation for 6 hours at 140 degrees Celsius. Now, for particular LIS loading, a known amount of LIS has been added and then it further stirred for 4 hours. The dope solution is then transferred to a blender. Now, a froth dispersion is produced by alternate blending and addition of non-ionic surfactant, polyoxyethylene octyl phenyl ether or Titan X100 to the dope solution. Now, after addition of 6 ml of this 6 ml of surfactant, the froth was then transferred to a plastic cylindrical molds. Now, the froths were then frozen and then cryo-desiccated to dehydrate the foams by sublimation of ice crystals. Acid-catalyzed cross-linking of the PVA of the foams produced were then done by soaking the foam in a solution composed of glutaraldehyde as your cross-linker and then hydrochloric acid as your acid catalyst and ethanol and water as your solvent. The samples were then thoroughly rinsed to remove the residual cross-linking solution and then finally dried. Now, as hydroxyl group rich polymer, hydrophilic PVA readily dissolves in water. Thus, cross-linking is done to your composite foams to render it stable and applicable in aqueous system. Now, FTIR of your sample shows that a broad OH stretching vibration peaks at 3,000 to 3,600 per centimeters is gradually decreased in cross-linked composite foams. Now, peaks at 1,700 peaks at 1,735 can be associated to residual aldehyde groups from glutaraldehyde which are left unreacted after acetalization. Now peaks, wider but broader peaks at 987 to 1,188 per centimeters can be associated to the CO group of the cross-linked polymers, which replace the 1,095, the intense peak at 1,095 of the uncross-linked PVA foams. Furthermore, the pictures here can shows to you the effective preparation of swollen yet aqueous stable foams as compared to the uncross-linked composite foams which readily dissolve in water. Now, the true and bulk density are expectedly increased with more addition of LIS loading, since the LIS adsorbents are denser than the PVA polymer. However, the total porosity decreases with LIS loading, which indicates that there is loss of voids in the composite foams. Now, the opposite porosity trends with the observed surface morphology was further elucidated through surface analysis. In the nitrogen adsorption-desorption branch of the pure PVA and the composite foams, it shows that all samples exhibited type 4 isotherm, and the hysteresis between the adsorption and desorption indicates that apart from the macroporosity of your foam, there is also mesoporosity. Therefore, the hierarchical pore network of our foam samples is composed of macropores and mesopores. Furthermore, the BET surface area increases with the LIS loading. This indicates that with the increase of the mesopore volume due to one, increase of the creation of the bimodal distributed mesopores, and two, the increase of the mesopore volume correspondingly increase the BET surface area. Now, the equilibrium adsorption results of the composite foams with different adsorbent loadings demonstrate the effect of PVA on the adsorption capacity of the LIS. Now, at initial concentration of 7 ppm, the LIS powder has a lithium uptake of 7.8 mg per gram, while the pure PVA foam has a minimal uptake of 0.1 mg per gram, which suggests that most of the lithium adsorption is caused by the LIS component. Furthermore, the adsorption isotherm of composite with varied loadings at varied initial concentration consistently showed the same trend as this figure, which indicates that as the LIS loading is increased, the lithium uptake approached that of the LIS powder. To determine the maximum capacities of the foams and to elucidate their adsorption behaviors, the widely used Lamois and Freundlich models were employed. Calculated isotherm constants are shown here in this table. It reveals that the lithium uptake of the LIS in composite foams are better characterized by the monolayer Lamois type adsorption than the Freundlich. Now, this result is consistent with those reported by the previous studies, and also verifies the chemisorption of the lithium ions by the LIS concomitant with the release of the H plus into the solution. And then, for the reusability of LIS PVA foams with high loading, while the composite foams with the highest LIS loading exhibited the best lithium adsorption, the selective extremely low fraction of PVA means lower sites for cross-linking, which could compromise the durability of our foam samples. Thus, performance of foams with highest loadings were evaluated through cycled adsorption-desorption test while examining their mechanical stabilities through repeated mechanical and flexibility analysis as shown in these figures. After several cycles, you can see that there is no decline on the adsorption capacity of 200 and 250 weight%. However, for 300 weight% sample, the foam gradually deteriorated, hence no testing was further done. So durable foams are those with preserved by physical integrity, that is consistent water absorbency, consistent percent volume expansion, and consistent compression force needed to the water after repeated use, all of which parameters were evaluated in this experiment. And to conclude, the following statements were adjudged. First, successful devised methods of combined surfactant blending, cryo-desiccation, and cross-linking gives us successful result for the preparation of a case of hydrophilic foams. Proper selection of hydrophilic matrix and employment of an effective preparation were equally important to minimize the effect of polymer matrix. Among the prepared foams, 250 weight % composite foam was found most suitable in terms of absorption, performance, and durability. The developed composite foams could be practically used for lithium mining from secondary sources. And lastly, application does not require energy-intensive processes like pack, bed, and membrane system, which makes us conclude that this could be better than other those reported. Thank you, and I'm ready for your questions if you have.